think you can hear me.
It's on now.
Oh, okay, thanks. How did you know?
It was a guess.
Okay. All right, good morning, everyone. I'd like to welcome you to our next session, Making ORAT Go Further. Please help me welcome our speaker, Patrick Wardle, founder of the Objective-C Foundation. At the end of the talk, you'll have the opportunity to ask some questions. Please use the microphones in the hallways. Thank you.
Thanks, Gia. All right, aloha and welcome to my talk on making ORAT go further. Normally I thank everyone for attending at the end, but I want to start by doing it now, especially since it's early, so thank you so much. Really appreciate and stoked that you're here. So a brief disclaimer, I haven't read this, but it's a required slide. So who am I professionally? My name is Patrick Wardle. I am the founder of the Objective-C Foundation. You might be familiar with some of my Mac security tools, the Objective-C tool suite. I'm also the author of the Art of Mac Malware book series and the organizer of the Objective by the Sea conference. So those are my professional accolades. Unfortunately, outside the cybersecurity community, I'm known simply as a paddleboarder. And this unfortunate label came to fruition earlier this year. I had an encounter, let's say, with a shark, and the most traumatic part of that was not battling a large shark on the high seas, but rather being branded as a paddleboarder. And the reason this is borderline offensive is because I consider myself somewhat of a surfer, and us surfers, we really don't like paddleboarders. And they fall and get in the way. And so, I was a little bummed about this, and, my friends all laugh at me, and my friends, speaking of, they don't really know what I do, but my one friend who knows I talk at conferences said, Patrick, what you should do is get up on stage and just tell people you're a paddleboarder. And I laughed, but in my head I was like, oh, that's actually good. And so, I'm going to go with Patrick the Paddleboarder from now on. So, what is Patrick the Paddleboarder going to talk about today? So what we're going to do is we are going to comprehensively analyze a rather interesting piece of Mac malware known as ORAT. Now, talks on malware analysis are generally interesting, right? The goal is often to find out the capabilities of the malware, but to me that's a little single-dimensional. I wanted to talk this a little more multifaceted. So what we're going to talk about is, in a sense, a somewhat novel, or at least underutilized in my opinion, analysis technique that can be applied to not only this malware sample, but essentially any malware sample. So in a nutshell, what we're going to do is we're going to talk about how to analyze a piece of malware by creating a custom command and control server that then allows us to kindly coerce the malware to reveal its capabilities to us by simply asking the correct questions. Again, kind of the takeaway from this is this should be generically applicable to a lot of other malware specimens and malware samples, and kind of an interesting approach. So we're going to start with some background information. We're going to highlight the configuration and the protocol of the malware. As we'll see, these are prerequisites that we need to fulfill before we can then build our custom command and control server and reveal ORAT's capabilities. All right, let's start with some background information. So the sample we're going to be talking about today, as I mentioned, is called ORAT. It's the focus of our analysis today. This was originally discovered by Trend Micro. They uncovered a new APT group, and along with that, some new Mac malware that this APT group was using. Now, both Trend Micro and SentinelOne performed some initial triage on this sample, which I wanted to mention because we're going to be building on top of their triage today. So giving some credit where credit is due. Now, both of these reports from Trend Micro and SentinelOne were great, but they really, in my opinion, stopped pretty far of where I wanted to get. So they were really more of a triage of the sample. So yes, they touched on the infection vector, the configuration, and speculate as to some likely capabilities, but they didn't go as far as even confirming those capabilities. And I reached out to one of the analysts who performed that, good friend, and he basically, as we can see on the slide, said, yeah, I did some initial triage, but when I tried to get the malware to run to confirm its capabilities, it kind of just exited and stopped. And so a lot of my analysis was somewhat speculative or based on static analysis. So what I wanted to do is take that further, because anytime any Mac malware comes along that's brand new, especially when it's attributed to a new APT group, that's a great opportunity, this will be one of the takeaways of the talk, for us to dive in and see what APT groups are doing in the Apple ecosystem. So then our approach was, yes, to kind of gain a comprehensive analysis of this malware specimen, but as I mentioned, do this via a custom command and control server. So here's the conceptual overview of what we want to achieve today. So the idea is we're going to run the malware on an infected machine, and after we have reconfigured it, it's going to connect out not to the attacker's command and control server, but now to ours. This will then allow us to, once we understand the protocol, task the malware and see exactly what it does. At the same time, we'll be running monitoring tools on the infected host, so when we execute a command that maybe we don't know or fully understand what it does, we can see. So if there's a command we might think lists the processes or spawns or executes something, if we run a file and process monitor on that infected system, we can see when we send that command to the malware, if it reacts in the way we expect, we can then understand. Also then, the malware will be sending its results back to us on our command and control server, so again, we can confirm and reveal the capabilities of the malware. Another big takeaway of this is, in my opinion, a much more effective approach than fully reverse engineering a sample. So again, some of the benefits. Traditional approaches to malware analysis, while sufficient, are very time-consuming. If you've kind of really gone down the rabbit hole of reverse engineering a malware sample in, say, a disassembler or a debugger, it takes a lot of time. Also, and this maybe not as the main takeaway, but this is something I kind of like as a side effect of this approach. So once you've analyzed the malware sample and build a custom command and control server to talk to it and task it, well, what you have is a complete cyber capability that perhaps you could use in offensive operations, let's say, hypothetically speaking. And the benefit of this is not only did you not have to write the malware, that's great, saves you time. It's also already been tested in the wild. Check, right? We all hate testing. And most importantly, if you're a offensive-minded cyber actor, let's just say, there's a great amount of plausible deniability. So if Patrick takes ORAT and now deploys this with his custom command and control server, which of course I would never do, if this was ever discovered, this would not be attributed back to me, but rather to the original authors of the malware. So there's a lot of plausible deniability. This is something I can say that I know certain actors do. And also, maybe this is just great for testing your EDR tools if offensive cyber operations aren't really your thing. So again, something to think about. Now, we mentioned there's some prerequisites for this approach, right? We can't just run a malware sample and expect it to randomly talk to our command and control server. We have to first reconfigure the malware so that it connects out to our server. And yes, you might be able to do this via the network easily, host files, DNS redirection, et cetera, et cetera. But again, if you're going to deploy this in a testing environment or some foreign network, you're going to want to figure out how to do this persistently. So we're going to talk about how to reconfigure the malware. So instead of talking to the attacker's command and control server, it connects out to ours. Obviously, we'll also have to understand the protocol of the malware. Pretty much every malware sample has different protocol. So we are going to have to do some initial triage of the binary to understand the tasking parameters that the malware expects, so that when it connects out to our command and control server, we can correctly task it. And then finally, we're going to need, as I mentioned, monitoring tools on the infected host. So as we task the malware, we can passively observe. Good thing is I've written a lot of open source malware analysis and monitoring tools for Mac OS. I've been doing this for a while, so that's kind of already checked off there. All right, so let's start with a triage. Anytime you're looking at a file, whether it's malicious or not, if you suspect it's malicious, it's really good to do some initial triage. And the main reason for this is that most analysis tools are file type specific. So if we do some basic triage, we can grab some hashes, we can use the file command to execute it against this malware specimen, we can pull out embedded strings, grab code signing information. End result, we see that we have an unsigned packed 64-bit Mach-O binary. Mach-O being the executable file format of Mac OS. So the main thing is really that file type indication, knowing that it's a Mach-O binary. We're now going to use analysis tools that can understand, can parse, and interact with Mach-O files. Right? If this turned out to be a Python script, we would use other analysis tools. In terms of the embedded strings, this is a great way to gain some initial insight into a binary pretty quickly. Here we can see that the binary has been packed with UPX. When a sample is packed, the first thing you almost always want to do is unpack the sample. This is because packed samples are going to be obfuscated and encrypted, and thus are going to hinder your continued analysis. Turns out that ORAT, which is in a binary called Darwin X64, so we'll see that on the slides, that's the ORAT executable, is packed with UPX. The great thing about UPX is you can simply re-execute UPX with the -D flag, and that will decompress, depack, unpack the sample for that. So we go ahead and just unpack the sample. We can see that succeeds, so great. That means all the packer obfuscations have now been stripped away. Interestingly, though, the unpacked binary is almost 10 megs. That's huge, and we'll get to why. Now that we have an unpacked binary, we can perform a few more additional triage activities. So first, we can use OTool to look at any dependencies. This is something I often do when I'm analyzing a suspected malicious sample, because it shows you what dynamic libraries a sample is linked against, which can tell you a lot about its capabilities. So for example, if it's linked against the AV Foundation framework, probably means it's trying to access the mic or the webcam. If it's linked against disk arbitration, it might be trying to sniff files off USB drives. In this case, though, we run OTool with the -L command to extract dependencies against the unpacked ORAT binary. And very surprising to me, there's literally no real dynamic dependencies other than the standard system ones. And this is strange, especially for what I thought was a fully featured APT implant. However, if we then run the strings command again on our now unpacked binary, a lot of very interesting strings fall out, including what appear to be paths to static dependencies. And based on their names, we can make some assumptions, which we will confirm, that show us that these dependencies might give the malware networking capabilities, daemonization capabilities, and things related to cryptography. Also a takeaway, from the embedded strings to the paths of the static dependencies, we see a lot that have the word Go in them. So we might start thinking that, well, maybe this malware is written in Go. So now we're going to go off on a brief tangent to briefly talk about reverse engineering Go binaries. And the reason we need to do this is there are certain challenges or nuances that you will face when reverse engineering a Go binary. And if you understand these, it makes the analysis process way easier. Now, this is not a talk about reverse engineering Go binaries. That could be a whole separate talk unto itself. So I wanted to list some really helpful resources on this slide that provide a great start to reverse engineering binaries that are written in Go. Also, these were very helpful to me. I'd never reverse engineered a Go binary before, and so these resources were very helpful. So thanks to these authors, hugely helpful. Now, the other reason we need to talk about reverse engineering Go binaries, besides their complexities and nuances, is this is actually becoming fairly common on macOS. So if we look at various macOS intrusions, malware attacks, et cetera, we can see that a decent percentage of them contain binaries that are written in Go. So I've listed a few on the slide. We can see things like Go agents that have been used in supply chain attacks targeting macOS, adware, other remote administration tools, et cetera. So Go binaries on macOS are becoming fairly common. Now, the first question you might have is, well, how do I even identify that a binary I'm looking at was written in Go, so I then know to work around some of the challenges I might face? And this is a great question. Turns out, though, it's very easy, for the simple fact that the Go compiler will add a Go build ID string into every Go binary. So if you just run the strings command and you see the Go build ID string, you know more than likely this binary has been written with Go. You can also load it into a disassembler or a decompiler, and if you look at the entry point of the binary, you will see it call into the Go runtime. So pretty easy to either statically or dynamically determine if a binary has indeed or originally was written in the Go programming language. Now, the first challenge we will face when reverse engineering a Go binary, for example, ORAT, is its massive size. So remember, we unpacked ORAT, and it was 10 megs. That is pretty big for malware. Most malware that's written in C, Swift, Objective-C is going to be, a meg max, perhaps. Having something that's 10 megs is like, that's a lot, right? This makes sense, as Juan articulated, who is one of the authors on the Go tutorials I mentioned earlier. And as he says, the reason that these Go binaries are so massive is that the Go compiler statically links in all the Go runtime binaries. And so we can illustrate this by creating a simple hello world program, compiling it, and seeing that it's over 1 meg. That's huge, right? If you do this in C, it's going to be a few KB in size. But the Go compiler, again, adds in all these static dependencies, and so you get a massive binary. So the challenge is, when you're reverse engineering a binary that was written in Go, is to kind of ignore all the static dependencies. Like, you don't want to spend hours reverse engineering some open source networking library. Even if it's closed source, like it's a networking library, it's going to make network requests. Like, you're more interested in how that library is used, right? What is the command and control server that the malware is passing to the networking library to connect out? So again, really the goal is you want to identify the latter, those static dependencies, and then ignore them so that you can focus your time and efforts on the malicious code. Another problem when reverse engineering Go binaries is that Go strings, once they are compiled into the binary, are not null terminated. In C languages, C, Objective-C, and even things like Swift, I believe, strings are normally null terminated. They have a 0 or null character at the end. Reason this is important to note is that a lot of reverse engineering tools, such as disassemblers and decompilers, struggle with this. So as we can see on the slide, I've decompiled the hello world or hello RSAC binary. And if I fire up a disassembler and pull in the binary to reverse engineer, we can see that there's a call to the print function. Awesome. But the decompiler doesn't know what string is about to be printed. And yes, we can manually go to that cross-reference and see that string, but since it's not null terminated, the disassembler doesn't display that in line. So this is kind of annoying because a lot of times when you're kind of perusing through disassembly, it's really helpful when there are embedded strings directly in that. So just something to be aware of. And this is also why an approach like we're talking about today, where in some senses we're simply running the malware and then observing its actions, are great because we don't really have to struggle too much with these challenges of the Go runtime. Now, before we get back to ORAT, I want to briefly also talk about another topic. Again, I'm trying to make this talk a little more multifaceted, and that is virtualizing macOS on Apple Silicon, because if you're doing Mac malware analysis, you're either going to be running on a dedicated analysis machine or more likely on a virtualized macOS VM. So I was a big fan of VMware, right? VMware Fusion worked great on Intel-based Macs. As soon as Apple Silicon came along, VMware was like, good luck. And yes, you can virtualize, I think, Linux and Windows on Apple Silicon using VMware, but like that doesn't help me. I want to virtualize macOS on a macOS system that's running Apple Silicon. So Parallels, another virtualization product, jumped to the forefront and said, hey, we will build you a pre-built macOS image, and I think they work with Apple. And when you're installing Parallels, you can simply download this pre-built image, and then you will, half an hour later, have a beautifully virtualized instance of macOS that's, ARM64 running on your Apple M1 or M2 system. This is great. Now, that might have sounded like a sales pitch, so I'm going to flip this on the other side and talk a little smack about Parallels. So while I was installing it, I noticed, unsurprisingly, it asked for my credentials, as the majority of installers do. And this is not necessarily a problem, but I've done a lot of talk and research showing that the majority of installers do so insecurely. And so, I'm always like, unfortunately, I think it's because I used to work for the NSA, anytime I see something, I'm like, ooh, can I break this? So I'm like, have that mindset. So when I see an authentication prompt, I'm like, I wonder if Parallels is doing this securely. Specifically, I wondered if a local unprivileged attacker or a piece of malware running on a system that didn't have root privileges could subvert this process to gain root access. And so I simply fired up a process monitor and ran the installer and watched what it did, right? No rocket science here, no crazy reverse engineering. Just watched what processes and files the installer was doing. And the first thing I noticed is there were processes running as root. This is unsurprising because the installer has just asked for root permissions, as most installers do. So again, nothing too bad there. However, I noticed that the process that was running was owned by the user. And this could be problematic because anytime a process is running with root privileges, but its file permissions are owned by the root user, this means a local unprivileged attacker or piece of malware could, in theory, modify that file. Right? Normally, you only want root processes running on files that are owned by root, just standard ACLs privilege-based stuff. However, maybe the parallel developers thought this wasn't a problem because the files that were owned by user but running as root were executing off a read-only disk image. Okay. So I was like, well, can I just remount this disk image and subvert the files? And unfortunately, the answer was yes. So 5 steps. This is how you could trivially and 100% reliably subvert the the Parallels installation process to elevate your privileges to root. And again, this is something a local attacker who didn't have privileges could do, or a piece of malware that was already running on the system who wanted to elevate their privileges to root to do more problematic actions. So let's walk through this quickly. First off, this unprivileged code could detect that the disk image was running. It could then stop the installer by sending it a SIG stop message, and this would be all transparent to the user. It could then remount the disk image as read-write, which then meant it could modify those user-owned binaries that were about to be executed by root. It would then resume the installer application, and once the installer displayed that authentication prompt, which the user would then provide their credentials because they are installing the software, you would have root. So this was great. I reached out to Parallels, or they reached out to me, and it's just like classic. I'm like, this is 2023. Like, why are we still having these discussions? So first off, they're like, the developers are denying that this is possible. And I'm like, really, y'all? Like, OK, here's the proof of concept. Like, run this. And then about 6 months later, I'm like, hey, so where are we on this? Is this fixed? I love using Parallels. I want to make sure, though, it's secure, though. And the security engineer I was working with, he was awesome. The rest of the company, room for improvement, let's just say. And so this was the email, and they basically said, well, you know, because I was like, is this fixed? Are there release notes? Is there a CVE? I don't really care about collecting CVEs. I mean, sure, that's great, but like, this is really good for other organizations to know, hey, do I need to install this update because it fixes some security issue or not? And they said, well, the installer is not a standalone product, so yeah, no CVEs, no release notes. And I just laughed at that. I was like, come on, y'all, like, I think we can do better. So the good news is, yes, this is fixed. The bad news is, though, like, I guess silently is a takeaway. All right, so thank you for those tangents. We will now get back to talking about ORAT and start by talking about its configuration information. Because as I mentioned, we need to reconfigure the malware so it talks to our command and control server. So first up, the Trend Micro report did provide some really helpful information, which was the configuration for the malware is embedded at the malware's end as an overlay. I mentioned that it's encrypted and that the encryption key is found in this overlay as well. And so if we load the malware in a hex editor, we can see, yes, at the end there's this encrypted blog, then there is an AES decryption key and the size. Now, one important thing, and this tripped me up for a minute, is when you unpack a binary using UPX, even if you tell it to preserve any overlay data, so that's data at the end of the file, UPX on macOS ignores this. And so that encrypted configuration will be stripped away. So I was having a problem where I would unpack the malware and then run it in my virtualization environment on Parallels after I got root. And it would exit, and that's because that configuration information was gone. So what I had to do was just manually prepend it. So again, just something to be aware of if you're dealing with UPX. It's going to strip out any data that it finds at the end of the file. OK, so now that we know we have this encrypted blob, we know it's AES, we have the decryption key, which is embedded in that, and a size, it's trivial for us to write a decryptor to pull out the configuration information. So here's the decryptor. It's my second program written in Go. The first one was that hello RSA. So if you're like a Go developer, don't judge me. I have no idea what I'm doing. But we can see that this works in decrypting the binary. So in a few steps, we basically initialize AES. Turns out that this was encrypted in GCM mode, which is some counter mode, so we have to utilize those API functions. We then extract the nonce, which is part of this encryption approach, and then ultimately invoke the GCM open command to decrypt that. And when we do that, the decrypted configuration falls out. So let's take a closer look at that to see what the malware has in its encryption configuration file, because again, this is something that we want to reconfigure. So first off, it's just a JSON blob. This is great. We can see there's some local information. This is useful or utilized when the malware is executing in gateway mode. But we're most interested in that second chunk, which is the C2 dictionary, which contains a network key and an address key. The network key, as we can see in the table below, can be set to 3 values that control the network level protocol that the malware will use. So it can either be plaintext TCP or UDP encrypted. And then, of course, there's the command and control server address, which is great because if we modify that, in theory, it should talk to us. So what we do is we take that decrypted JSON blob. We just add that new address of our command and control server. Here it's that 192.168 address. Then we take our Go encryptor and basically reverse it to now re-encrypt the new configuration. So there's the code to do that, about 15 lines of Go code, re-encrypt the new config, and now we then append it to the malware. And so if we dump it, we can see the new encrypted config. It's encrypted now, so not much to see. But more importantly, when we execute the reconfigured ORAT binary now, it connects out to our command and control server, which is great. So I just started a netcat listener on the specified port and IP address where my custom command and control server was running, ran the malware in the virtualized environment, and success, it connects out. This is great. We're making progress here. I briefly triaged some of the malware's disassembly and noticed that you could actually reconfigure the malware using various malware-specific environment variables. So as we can see on the slide, it queries various environment keys. You can see it calling getEnv, which is the API to get environment variables. And it turns out it looks for 3 different environment variables that, if specifies, will override the configuration, will the encrypted configuration. So the RKNet allows you to specify the network level protocol. The RKAdder, the address and port of the command and control server. And then it actually also supports a debug flag, which makes analysis way easier. So this is great for testing. But again, if you're going to do some more maybe redeployment of this, you're not going to use this because these are environment variables and thus by definition are temporary. So here's an example of that just to show this actually works. We load the malware in a debugger after setting 2 of the environment variables that it's looking for. And then later on, we can see that, yes, indeed, it's using those values from the environment variables, not the ones from the config. So again, this is just a great way to kind of on the fly reconfigure the malware, especially when you're doing some initial testing. OK, so now we have the ability to coerce the malware to talk to our custom command and control server. This is great. We saw it connected out to our netcat listener. Hooray, hooray. But now what do we do, right? The malware's like, hi, I'm here. We need to know how to respond. And in order to do that, we need to understand the malware's protocol. So now let's talk about the protocol that ORAT uses so that we can task it. Now, if you looked very closely on the netcat slide, or the netcat listener a few slides back, you might have noticed that when the malware connected, before the HTTP post request and standard HTTP-looking content, there was a question mark. And the question mark basically means that netcat received some binary data, and it didn't know how to display it, so it just put a question mark. And so there's something slightly strange going on, right? We're not just getting plaintext HTTP data. So I pop back into the disassembler, and I look for some static dependencies on some networking, and I noticed that there was a reference to a library called smux. And smux is open source, as are the majority of the static dependencies in this malware, which means we can hop over to GitHub and see what it does. So I put the README on the slide. Basically, it says that smux stands for simple multiplexing, and it is a multiplexing library for Go. So what is multiplexing? Well, I learned about this in my networking class in college and then forgot about it. It's a pretty obvious concept that many of you are probably aware of, but let's just re-articulate it here to make sure we're on the same page. So multiplexing is the idea of taking multiple streams and combining them all into a single session or stream or connection, sending that over to the server, and then on the flip side, the server will demultiplex these streams and pass them on to the various endpoints server side. Now, the obvious reasons to use this is it's very efficient, right? Instead of having multiple connections for each component of the malware, you're only going to have one. So, for example, we can see this if we fire up a network monitor. There's only one connection, even though the malware is sending out heartbeats, command and control server tasking, exfiltrating files, all in parallel. This stuff is all multiplexed over one single connection. And the reason this is all relevant, other than a refresher on multiplexing, is that this means our custom command and control server will have to multiplex aware, because all the malware streams are going to be multiplexed over this single connection. So let's now dive into creating this custom command and control server. And as we go, we'll talk a little bit more about the protocol as well. So I just mentioned that the command and control server we're creating has to be multiplex aware. So what we're going to do is we're going to use that same smux library because it's already written and that's the one the malware is using. So it makes sense on the server side that it also is going to use the same one. Since it's open source, we can just download and install it. Again, I didn't even know how to install a Go dependency. Turns out you just type go install and then the path. And then you add it as an import. So the next thing we're going to do on our custom command and control server is open a listening socket. This has nothing to do with multiplexing yet. This is simply how you create a listening socket in Go. About 10 lines of code. We open a listening socket. We accept the connection, and then we will handle the connection. And if we compile this and run this, we see that the malware, as kind of expected, connects to us. So instead of now using Netcat, we've just created some Go code that will accept connections. So now, though, let's deal with the multiplexing, because as I mentioned, ORAT is going to client-side multiplex all its connections over a single stream and then send that to the server. So this is where we're going to use the smux library, see invocations to its APIs. We initialize the mux server, accept the mux stream, and then handle the stream. If we recompile our custom command and control server, relaunch the malware, we see now not only does it connect in, but our command and control server can handle things, for example, pull out the stream ID. So again, making great progress. Still, though, we have to talk about the protocol. All we've done now is created a MUX-aware command and control server that any code can connect to. But to figure out what questions to ask the malware, because again, our main goal of this talk is to figure out the capabilities of the malware by just asking it the right question. Luckily, the Trend Micro researchers touched on this, and they described a very interesting tasking mechanism that the malware uses, which is that the malware creates a local server on the client side, and then as requests come in from the command and control server, either the attacker's one or the custom one that we're creating, it will map those to something called routes and then execute the code that maps that. So we'll dive into this a little more. If you're like a web or full stack engineer, this probably all makes sense to you. I'm not really a software engineer, so this took a minute for me to wrap my head around. But the idea is the malware is essentially going to spin up a local server, again on the client side, and it's going to register routes, which are simply API endpoint requests mapped to chunks of code that'll execute when it gets a specific request. Then as these requests come in from the command and control server, it will find the matching route and execute the logic. So here's an example of that. If we look at the malware's code, again, we don't want to dive into the binary that much, but if we triage it, we see that it's using LabStack's Echo server. LabStack is an open source lightweight server for Go. Again, the malware authors just grabbed this, compiled it into their binary. And we can see the first thing it does is it specifies a route handler. So at number 1, where it says info.fm, that is a Go subroutine that contains the code that the malware will execute for this specific request. Step 2, in the disassembly, we can see it specifies the route request verb. This is going to be get or post. Here it's get. Step 3, it specifies the route request. This is the actual API endpoint that the malware is going to expose and expect for tasking. And then it finally registers this with the echo.add API command. So here's an example in a disassembler that hopefully will also shed some more light on this. If we run the malware in a debugger, connect to it, and make a request, it will look up the request we're making, and if we make the correct request, which we'll talk about in the next slide, it will find the correct handler and then invoke that. So again, all it's doing is taking requests, mapping it to code, and then executing that code. And if we look at the backtrace, we can see this is exactly what it's doing. This is handled when an incoming request comes in from our command and control server. It calls the router.find method to find the correct handler for this request, and then we can see it executes it. So what are some of the routes that the malware exposes? Again, these are the API endpoints that the malware is exposing client-side that we should be able to task from our command and control server in order to get the malware to perform its action. Well, lucky for us, the malware authors didn't obfuscate or strip any of these strings, so we can pull them out of the disassembly very easily. And as we'll see, their names are fairly indicative of what they do. So that's great. So here's a list of them, and we'll go through them and perform some of these taskings. Again, this was just pulled out from the register routers API function. Now you might be wondering, okay, that was a pretty comprehensive list, but obviously some of those are going to take parameters. So how do we know which ones take parameters and what those parameters are? Well, again, pretty easy by briefly triaging the disassembly. So for example, one of the routes that the malware registers for is the /agent/port scan. Again, this means if we make that request from the command and control server, it'll execute what we assume is port scan logic. However, if we look at the disassembly for that, we can see it expects two parameters, which makes sense, right? It's the host to perform the port scan of, and the ports to scan, a range of ports. So now we have, just to review, we have talked about how to reconfigure the malware. So now it's connecting out to our command and control server. We've also talked about how it handles routing. Specifically, we extracted the routes that, in theory, we should be able to task from our custom command and control server so that the malware will perform the action so that we can confirm its capabilities. So let's now dive into this. The first question, though, and this took me a while to figure out, is how do we actually get the request, the route request, to the malware so that it triggers the capabilities logic so that we can then observe that and confirm that. So this kind of goes back to the Trend Micro analyst who said, hey, I kind of ran the malware. I saw it set up this local server, but then like nothing else happened. Like I sent it requests, and it just like ignored it, and et cetera, et cetera. And this kind of stumbled me too. I could see in a debugger that the malware was invoking the start server method of the Echo server, which is, again, is a standalone library that sets up a server. If I compiled this into my own program, it worked great. But when I executed it in the malware, and looked for listening sockets, like there was nothing. So I'm like, how do I connect to the malware to send it these commands? Well, in retrospect, duh, it has to be multiplexed. So basically, the malware was connecting out to me and expected the tasking to come back on that same multiplex stream. This meant that also then the malware, when it set up that server locally, that server was using that same multiplex connection. So there was no new listening socket. So this means that if you want to task the malware, you have to understand multiplexing and utilize the multiplex stream that the malware initializes when it connects out, when it checks in. Again, in retrospect, obvious. This is what multiplexing is. But again, I'm not really a software engineer, so clearly I struggle with some of these concepts. So here now we have our CNC server using the SMUX library, which we already talked about. But now we've added some additional logic to add our tasking back into the multiplex stream, which will then be sent back to the malware, which will then demultiplex that, look at what we've specified, and if it matches one of registered routes, it will execute that logic, allowing us to then figure out and understand exactly what its capabilities are. So 3 easy steps. Again, this took me like a week to figure out. So if you ever struggle with reverse engineering, I'm right there with you. We open the stream. This is the existing session when the malware connects out to us. We then task it by simply writing to that stream, and then we can read from that stream to receive any responses. So in some sense, embarrassingly simple. So now let's walk through, since we now have the ability to task the malware, to confirm its capabilities. Now, I will caveat that a lot of the registered routes are fairly verbose, like the port scan command probably does a port scan. But maybe we want to figure out how that port scan is performed. So again, now that we have this custom command and control server and we can task the malware, we can simply task it and then watch what it does versus having to reverse engineer all that Go code. Also, again, as I mentioned, you can use this technique for other malware samples. A lot of malware isn't necessarily this verbose in its tasking. You'll see that it expects, a number for a certain command. You might not know what command 2 does, but if you can task it, you can send it the 2 and then watch what it does. So let's walk through now some of the tasking with the goal basically of confirming and understanding the capabilities of the malware, which is the main goal here. So first off, we can send the /agent/info request. I assume this is something that allowed you, triggered the malware to perform some survey. And as we can see on the slide, this is exactly what it did. So from the custom command and control server, when the malware checked in, I basically said, hey, execute /agent/info. This will get mapped. First, it'll get muxed, sent to the malware, demuxed. It'll look up the /agent/info route, and then execute the logic with that and send the response back, which we can see is a pretty simple survey about the infected machine. But again, I didn't have to reverse engineer the survey logic. I just asked the malware to perform the survey, and then it sent back what its survey logic entailed. The malware also supports the ability to exfiltrate files. This is done with the /agent/download command. So if you make this request, that will map to the exfil route, the logic in the malware. You can see that on an infected system, I'm running a file monitor. I then sent the download command. So if this would download a binary from the server or download it from the malware to the server, exfiltrating. But via a file monitor and a network monitor, I could see it was opening the file I specified, and then it would send it back to my command and control server. Also, obviously, on the command and control server, I'm dumping the responses it sends so I can see the contents of the file. So now I very easily can confirm that the /agent/download route maps to exfiltration. There's also a screenshot command. I was super interested in this. I was like, how is it going to perform screenshot logic? Executed it, came back and said, sorry, not implemented on Mac OS. So again, saved me a lot of time from having to reverse engineer to ultimately figure out that this is not implemented. The malware simply told me that fact. It also supports a /agent/get command. This is one of the commands I didn't know what it did. And again, I didn't want to reverse engineer it, so I just executed /agent/get and watch what it did. Turns out it's a tunneling capability, which is kind of neat. So on the slide, we have the infected system in the middle, the custom command and control server, and then another system that presumably is the other tunnel endpoint. And what you can do is you can specify a host and a port, and it will actually then set up the infected system as a proxy or a tunnel, allowing you to tunnel traffic through it to another host. You can see this might be useful where you install the malware on a beachhead system, on an enterprise network, and then all the internal hosts don't have to actually make outgoing connections. They can just talk directly to this one specific system that has been set up in tunnel mode, and then that gets tunneled out to the attacker or your custom command and control server. So a neat feature, something we don't normally see in malware, but for APT grade malware, kind of makes sense. Now we come to the port scan option tasking thing. Again, we assume it's a port scan, and yes, no surprises, it is. But we can observe how they're doing the port scan by firing up a network monitor. I wanted to do, are they doing some crazy port knocking, port thing? No, they're just trying to open a connection to the specified port. And if it's open, it'll respond back to the command and control server. So I gave it a range of ports, tried to connect to each one of those on the host I specified. And for any that were open, we can see on the slide, it responded to my command and control server saying, OK, port, for example, 123 on the host you specified is open. Finally, the malware also has the ability to self-delete, which is, again, a kind of a neat feature. Not something we see commonly, but again, APT malware often has this. The idea generally is if one of its victims is compromised, it can quickly maybe deploy this to remove itself from other victims without maybe revealing the scope of an infection. So again, I didn't have to reverse engineer how the malware killed itself. I could just task it with the kill self command, and then by running a file monitor and a process monitor on affected hosts, I could see that first the malware self-deleted and then terminated. Not too surprising, but now we know exactly how the malware self-deletes. And then, of course, the client disconnected because it's killed itself. All right, so let's start by wrapping this all up, or I guess end by wrapping this all up. So some actionable takeaways. First, and I mentioned this earlier, anytime a new APT group is discovered, especially if they have brand new Mac malware, this is a great opportunity to study what attackers are doing in the context of Apple ecosystem. And this is especially important on Mac OS because there's not a ton of APT Mac samples that we have access to. The question is always not targeting Mac Enterprise, are we detecting it? Combination of both, in my opinion. But regardless, when we find a new Mac malware specimen that's attributed to a decently sophisticated APT group, it makes sense to comprehensively to understand their tactics and see if our defense will hold up. Now, one of the main takeaways, of course, is that a custom command and control server is a neat, interesting, and in my opinion, pretty efficient way to understand malware by simply tasking it, which I think is kind of cool. So, maybe try this out with your own malware samples. If you come across especially a particularly large Go sample that you don't want to waste your month reverse engineering, like figure out, hey, can I create a custom command and control server, and then ask it and have it reveal its capabilities to me? And the answer might be yes, in a way that would be way more efficient, and in my opinion, interesting, than reverse engineering all its binary code. And then finally, I think it's kind of neat as well, we have a malware sample that we now intimately understand. We have some command and control server that can task the malware, like go play, right? Or go test, I should say. Now, if you're interested in learning more about Mac malware, I've actually written an entire book on this. It is 100% free online. It's kind of like an open source book. Although you can buy it as well from No Starch Press. 100% of the royalties go back to the Objective-C Foundation, so you are supporting a good cause. And actually today I was invited to do signing at the RS bookstore. So I will be there at 12:30 to 1 today. Stop by, I'll sign a book, we can talk about sharks, malware, whatever, hang out. Also, as I mentioned at the beginning of the talk when I was talking about my professional accolades, I also organized the Objective by the Sea Mac Security Conference. And it is a conference dedicated to Apple security topics, macOS, iOS. Next one will be held in Spain. We're actually up to version 6.0, so we've really kind of got it nailed by now. But it's a great community, single track talks, track all about Apple, macOS. Also, it's on the coast, Mediterranean, Spain. So check it out. See if you can get your company to send you to Spain. And then finally, I briefly want to thank the companies that support the Objective-C Foundation. So everything the Objective-C Foundation does is nonprofit, so free open source tools, free books, conference, my research, et cetera, really wouldn't be possible without these companies. So again, I just want to take a brief moment to thank them because they are really helping push forward a lot of Mac security research and Mac security defense mechanisms. So that is a wrap. I think we have 2 minutes for questions. If you have a question, please use the microphone. And if you don't want to ask a question, I'll be around for a few minutes after the talk if you want to come chat with me directly. But before we do questions, again, thank you so much for attending. Hope you are inspired to go out and write custom command and control servers. No questions? Oh, we have a question. Awesome.
So did you have to, I don't know if this, did you have to disable any of the built-in Mac protections? So, things like it won't even let you, a random executable open a file or directory unless you, gatekeeper all the other. Did you just disable all of that?
Yeah, that's a great question. So the question was, did I have to disable a lot of macOS's built-in security mechanisms to get the malware to run in the first place? And the reason that's a great question is because often you have to. I mean, we have seen Mac samples that are notarized, meaning Apple has given them their stamp of approval. inadvertently, albeit, and those will generally run, but in this case, this binary was unsigned, which means Gatekeeper wouldn't allow it to run. Gatekeeper is pretty easy to get around, but a lot of times if you want to do debugging, you have to disable system integrity protection. And we are kind of approaching this like unfortunate inflection point where like I spend a lot of time trying to like figure out how to like neuter Mac OS so that it allows me to run malware. Apple's like, you don't need to do that. I'm like, yeah, I'm a malware researcher, I do. You know, things like when Apple revokes the certificate, even if you try to run it. So you have to manually unsign it and then maybe re-sign it with an ad hoc signature just so you can run. So it would be great if there was a more comprehensive like malware analysis mode. Turning off system integrity protection is a great start. That kind of neuters a lot of things. But for example, XProtect, which is Apple's built-in AV tool, if there's an XProtect signature, like you're gonna have to like kill XProtect or re-signaturize the binary. So it is getting a little frustrating. So if anyone from Apple is here, I can't imagine there's like, you know, Mac OS now shipping with malware mode, but that would be great for me. So great question. Yeah, there is some things you have to do. Start with system integrity protection, and a dedicated system is probably the way to go.
And so why not just leave all the RK things set all the time, especially on an enterprise network, and point them to your honeypot?
Yeah, I mean, that would be a great idea as well. Go for it. Great question. Thank you. Any other questions? Yes. Do you mind grabbing the mic? I think they're recording too, so.
Thank you for a great presentation. I didn't understand that part. Usually when you run a virtual machine, you want to separate the client from the host. But in your case, you want you want that process to have the root access. Can you explain that one more time?
Yeah, sure. So there was, and this is my fault, there's basically two topics that we kind of muddied together. So the first topic is, yes, generally you want the virtualized system to be self-contained so you can run malware which wouldn't infect this. However, on the host, when you're installing the virtualization software, there is an opportunity for an unprivileged local attacker or some malware, if it's already on your host that maybe has surreptitiously infected your system. As you are installing the virtualization software, it can piggyback off that to gain root access. Does that kind of make sense? So it's separate from the virtualization machine. It's just the virtualization software itself had a privilege escalation vulnerability.
Okay, so you just discovered a bug in that
Yeah.
process. Okay.
Yeah, I poke on things in my free time. And so, yeah, like I said, anytime I run software on my system, I'm always like, is this going to make my system more secure, or insecure rather? And in this case, the unfortunate answer was yes. Even though, yes, the virtualization component was okay, and I could run malware safely, in the process, I opened myself up to a local privilege escalation vulnerability attack.
Okay.
Not
Thank you.
good. So this, again, TLDR, like, don't trust third-party software, especially if it's closed-sourced and hasn't been audited.
Thank you.
Awesome. Well, I think we're out of time. Thank you so much again. If you enjoyed the talk, I think there's feedback forms. These are super helpful for me as a speaker if there's things I can improve on, if you enjoyed the talk. So thank you for that. But again, also thank you so much for attending. Clearly, I'm very excited and passionate about this. So feel free to reach out, Twitter, email, in the hall if you want to talk more about this. And again, thank you so much for attending.